Like we had a work day on chapter 4, we're going to have a work day on chapter 6, and that's what today is. Okay, so here's the way this works. So let's resolve those three questions between electronegativity, structures, and bonding angles. All right? All right, we just got rid of nothing. Isn't that kind of cool? So with that, let's say I take a molecule like, let's do chloroform. Okay, so chloroform is carbon, 3 hydrogens, and a chlorine. That's chloroform. Right? Chloroform's a really nice solvent. If you put it on a little hanky, put it over your mouth, it'll make you loopy, and it used to be used as a kind of some type of an anesthetic with ether, and they put that over your mouth and then hack off your leg. So the whole thing with local anesthetics and general anesthetics has come a long ways. From biting a stick to ether to now we have something that can actually put us out while they're removing whatever it is they're removing. So chloroform being a very important one, we want to be able to use VESPR to predict the structure. What does this thing actually look like? What does the molecule of chloroform look like? So we start here. Maybe you start with the name, all right? Carbon trihydrochloride or something like that, right? We're using that, the non-ionic nomenclature for this thing. So this carbon has 4 electrons. Each hydrogen brings in 3 electrons. Chlorine has 7 electrons. How do I know that? How do I know that?
The valence shells.
Okay, the valence shells. And where up here do I know that?
Common red numbers.
Okay, the very, very top number, right? The one way out of the box. The 1, 2, 3, 4, 5, 6, 7. That's where that comes from. Okay, so that's the Lewis dot structure. So I have to account for these 14 electrons. So this equals 14 electrons. Okay? Good? Carbon's going to be the central atom. Hey, by the way, something I didn't mention when we dealt with electronegativity on Wednesday. The central atom is always the element that has the lowest electronegativity. Kind of a nice little easy rule of thumb. Hydrogen will never be a central atom. It can't be. It can only make one bond. So you don't have to worry about hydrogen. That doesn't play into it. So chlorine is 3.0, carbon's 2.5. Oh, carbon's the central atom. So carbon brings in its 4 electrons like that. Okay, so this is electron dot structure. Hydrogen brings in its electron. Hydrogen brings in its electron. Hydrogen brings in its electron. And then chlorine brings in its 7 electrons. So chloroform makes a really nice, so chlorine then brings in its electron, so it makes a really nice molecule. All right? So we draw the structure for chloroform without all these. We say it looks like this. It looks like carbon, chlorine, hydrogen, hydrogen. That's chloroform. Okay? So here's the thing. How many electron domains does carbon have coming off of it? Electron domains. 4. 1, 2, 3, 4. What's the farthest away 4 can be from a central core? What is it? 109.5, right? That's the tetrahedron. So we just have to memorize that 4 is tetrahedral. 3 is trigonoplanar. 2 is linear. I didn't bring linear today. Okay? So that's what that looks like. All right? So if it's tetrahedral, it's approximately 109.5. I'm not going to ask you exactly what it is. I gave it to you for ammonia and water, 107, 104.5, but it doesn't matter. It's around 109. That's all you need to remember. It's not 120. If it's 120, it's going to be trigonoplanar. Okay? So again, those bond angles, tetrahedral is going to be around 109. Trigonal planar is going to be around 120. Linear is going to be around 180. It's going to be 180 because there's nothing going to be in the way of that. So what we then look at is, are the vectors canceling each other out? So if you have a four-way tug of war, where all vectors are pulling equally, so I've now memorized my electronegativity, which is the atom's desire to have electrons within the context of a chemical bond. Remember that? So I know 2.1, 2.1, 2.1. I know 2.1. And what is carbon?
3.0.
2.5. Okay? So here's the thing. This vector has a delta En of 0.4, 0.4, 0.4, 0.4. Are those four bonds equal? If they're equal in their strength, then that means they're pulling on the central atom equally, which means the vectors cancel each other out. Therefore, methane is a nonpolar molecule. Okay? Back to chloroform. 2.1, 2.1, 2.1, 3.0, 2.5. So this bond is pulling slightly this way. This bond is pulling slightly that way. This bond is pulling slightly that way. But those are all equal. That's 0.4, 0, 0.4, 0.4, 0.4. But what happens to this bond? Yeah, this bond is actually pulling this way at 0.5. So that bond and these bonds are not equal. Therefore, the electrons are not being distributed around carbon equally. So what does that do to chloroform? Is it a polar molecule? Yes, it is. It's not very polar, but we would consider it polar. It's a nice solvent to work with. It causes nosebleeds and it's a little bit carcinogenic, but other than that, it's a pretty cool molecule. Okay? We used to work with it a lot in grad school. Okay, is that good? Questions on that? So this is called the Lewis dot structure. This is called my electron domains, or my electron domain geometry. If I'm 4, I'm tetrahedral. If I'm 3, I'm trigonal planar. If I'm 2, I'm linear. Okay. Other questions? Because that's really it.
What about trigonal pyramidal?
I'm not going to get into trigonal bipyramidal.
Okay.
Yeah, and if you want it, I mean, I'll teach it if you want. But the center core, it's kind of an interesting thing. It does this. It actually has what we call an equatorial plane and an axial plane. Okay, so it's a cool molecule. It has some really fun properties, and honestly, phosphorus does do this. It forms a 5-member bond, but I'm not going to take you there. Okay, that's general chemistry, and you've had it, but we're not going to go there. Okay, and an octahedral as well. Octahedral is when we have 4 around here. Yeah, it's so in general chemistry I go a little bit further, but we only need to go to the tetrahedron. I can only think of like 2 examples of where we violate that in this entire course. So why complicate it? Okay. Other questions before we make it a work day? Anything else that we go over in chapter 6? Because I'm done. And I hope the worksheet will help you kind of resolve how well you know this. So here's the thing with the worksheet, and I'll float around if you have questions. What I would do with this worksheet, we have about a half hour in here that we can have one-on-one or 1-on-53. It's set up so that I give you a couple different examples of the question. Maybe work yourself down like the first 2 or the first one So you can actually finish this and then do the rest later. This is to assess, do you understand the properties and what we learned out of chapter 6? Okay, if I were to give you a quiz, this is what it would look like. Okay? This is what the exam will look like. So if you're comfortable with chapter 6, you'll do fine on this. If you have a little work to do, well, this will assess that. Okay? So this is really kind of a self-assessment of, did you understand the basic concepts? Oh, hey, one thing I took out of this, you could cross out the molecular geometry down at the very bottom. You don't need that. A couple things I got here. So whatever, I'm good, very flexible. Okay. We'll work on